Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing OSPF, where we will review OSPF concepts, configurations, and troubleshooting in Junos. In this lesson, we're reviewing OSPF area and router types. So far, we've discussed single area OSPF, which is typically perfectly reasonable to use for networks. Once we have a sufficiently large network, though, we may find that changes in the network, or a flapping route, can have adverse effects on our network, particularly if we have many branch offices with lower power devices. So let's see why this is an issue. Due to the requirement that all routers within an OSPF area must maintain an identical OSPF link state database, if you have a large network, this can cause scaling issues. Routers which have limited CPU power may not be able to handle repeated LSDB changes, which occur often. This can cause negative effects, like high CPU utilization, and even cause the router to stop responding. Because of this, we need to have the ability to segregate our OSPF network into separate areas, so we can shield our branch office routers, which are typically lower in power and capability, from the rest of the network. This is where OSPF areas come into play. See, OSPF areas allow for the partitioning of routing information into smaller sections. As you can probably imagine, if we have a branch office with a router connected into the corporate network and only has a single connection into the larger network, it's unnecessary for that branch office router to hold the entire link state database for OSPF. With OSPF, route summarization may only occur at area boundaries. This allows us to maintain the rule that all routers within an OSPF area maintain an identical LSDB to all other routers within the same area. For OSPF, as opposed to ISIS, as we'll discuss in a later section, an interface is wholly in an area. This means a particular router may be a member of multiple areas. These routers are a special router type. They are called area border routers, or ABRs. There are other router types which we'll discuss in a following slide. Additionally, the area types we'll review in this lesson are shown here. We'll review the backbone area, also called a general area. This acts the same as a normal OSPF area. The special area types have certain rules for the types of link state advertisements which may be advertised into or from them. These areas are the stub area, not so stubby area, and totally stubby area. As we see in our diagram below, we have an OSPF domain with multiple areas, and the router in the middle is a member of both of the areas. So it's an ABR. It has multiple interfaces, part of Area 1, and a single interface, part of Area 0. Now, let's take a look at what other router types we can have in OSPF. There are 4 types of routers in OSPF, 3 of which we've already mentioned a bit or in detail. The DR and BDR are a type of router which represent a single broadcast domain. These are used in the effort to enhance the scaling of OSPF by limiting the unnecessary flooding of LSAs in an area. The next, which we've mentioned, is the ABR, or Area Border Router. The ABR is a router with interfaces in 2 or more areas. There is not a technical limit to the number of areas that an ABR may be a member of, though there may be a practical one based on the computational power of the router, dictating the size of the LSDB which it may hold on to, and the number of LSDB changes it can handle in a given time. The ABR will originate Type 3 LSAs and control which LSAs are flooded into any of the areas it is connected to. In our diagram, we see two ABRs are present, one at the boundary of area 0 and 1, and another at the boundary of area 2 and 0. The following router type is the Autonomous System Boundary Router, or ASBR. An ASBR is any router which redistributes routing information from an external protocol into the OSPF domain. This can be static routes or routes learned from another dynamic routing protocol. The ASBR will originate Type 4 and Type 5 LSAs. The Type 4 LSA contains information on how to reach the ASBR itself, and the Type 5 LSA contains the routing information itself that it is distributing into OSPF from an external source. In our diagram, we see that we have a single ASBR located in Area 0. This ASBR is connected to a router which is not a member of the OSPF domain pictured, and the ASBR is distributing the external routing information into its OSPF domain. The final router type is a standard OSPF router. This represents all other routers which are not DRs or BDRs, ABRs or ASBRs, and which participate in the OSPF domain. Now that we've reviewed the types of routers, let's dive a bit deeper into the different area types, starting with the backbone area. The backbone area is Area 0. In a multi-area OSPF domain, all areas must be directly connected to the backbone area. There is a way around this, however, using a feature called Virtual Link. This feature is not covered in the JNCIS ENT, though it effectively requires the creation of a tunnel, which tricks the OSPF into thinking the router is directly connected to the backbone area. Regardless of the presence of a virtual link, in order for traffic to travel from one non-backbone area to another non-backbone area, the traffic must traverse through the backbone area. This could mean that an ABR which is connected to the backbone and the two non-backbone areas performs the routing, though in order to maintain full connectivity between all areas in an OSPF domain, all non-zero areas must be directly connected to the backbone Area 0. In our diagram here, the backbone area is the blue area, Area 0. We see that the two non-backbone areas, Area 1 and Area 2, are both directly connected to the backbone area via the ABRs here. Now, let's take a closer look at the non-backbone areas, or general OSPF areas. General OSPF areas will only receive Type 3, 4, and 5 LSAs from the backbone area. Type 1 and Type 2 LSAs, the router LSA and network LSA, will not be flooded into the area. However, of course, the routers within the general areas will still originate Type 1 and Type 2 LSAs. Once the ABR receives the Type 1 and Type 2 LSAs, it will process the information and originate a Type 3 LSA into the other area. Outside of this specification, the non-backbone areas operate exactly like the backbone area. In a single area OSPF, it is not required for the single area to be Area 0, since we do not have any ABRs. However, once an additional area is added to the OSPF domain, Area 0, the backbone area, must be present to allow full connectivity between areas. In the following slides, we'll review these special area types, the stub, total stub, and not-so-stubby areas. First, let's review what we mean by a stub area. A stub area is defined as a stub on all routers in the area, However, the ABRs will use this to control the flooding of LSAs. If you're coming from the Cisco world, this is a very important and somewhat non-intuitive distinction. The stub flag must be present on all routers in the area on Junos devices, not just the ABR. The ABR, being the gateway between areas, controls the types of LSAs that are allowed to traverse the area types. In a stub area, external route information is not allowed. Therefore, Type 4 and Type 5 LSAs are not flooded into an area from an ABR. Similarly, Type 4 and Type 5 will not be flooded into the backbone area from a stub. Only Type 3 LSAs are flooded from the backbone area into the stub area. When external routes reach an ABR from the backbone area and the ABR is connected to a stub area, the ABR will originate a Type 3 LSA with a default route to allow the stub to reach the external routes. In our diagram, we see that Area 2, the green area, is marked as a stub. This would be identified on the ABR's configuration to identify this area as a stub, as well as all of the routers within the area here. Since the ABR is the gateway to the area and the controller of LSA flooding to and from the area into the rest of the OSPF domain, it must also have the stub flag configured. Now, let's see how this differs from a total stub area. In a stub area, Type 3 LSAs containing routing information for all of the OSPF domain are flooded into the area. However, let's say we have a branch office which only has a single connection into the rest of the OSPF domain, and we're using a small router there without much CPU power, because it's a small branch office. In this situation, there's no need to advertise any more than just a single default route to the area. In this case, we'd use a total stub area. In a total stub area, only a single Type 3 LSA is advertised from the ABR, which contains a default route. Like in a stub area, ASBRs are not allowed in the total stub area. If a Type 4 or Type 5 LSA reaches the ABR from the total stub, the LSA will be dropped and not flooded into the rest of the network. In our diagram, we see that Area 1, the orange area, is marked as a total stub. This would be identified by the configuration on the ABR connecting the area to the rest of the OSPF domain. Where all of the participating routers in the area would have the stub flag, the total stub would be identified on only the ABR. In each of these area types, we can have more than a single router connecting the area to Area 0, in which case the IGP metric would be used by each router to determine the best path to the nearest ABR. Finally, let's take a look at the strangest sounding OSPF area name, the Not-So-Stubby Area. The Not-So-Stubby Area, or NSSA, works exactly the same way as a stub area. However, ASBRs are allowed to exist in the NSSA. If perhaps we have an area that we still wish to shield from the rest of the OSPF domain's LSA flooding, but we have some external routing information that we still need to propagate into OSPF, we can use the NSSA area type. When the ASBR sends LSAs into the area, it will send them as a special LSA type, Type 7. These are LSAs which are identical to Type 5, though are used to allow external routing information to traverse an NSSA. When the Type 7 LSAs with the external routing information reaches the ABR of the NSSA, the Type 7 is converted into a Type 5 LSA and flooded to the rest of the network. Now that we've reviewed the various area and router types, let's take a look at how to configure OSPF and these area types. As we see in this configuration example, we have 4 areas configured on the single router, making this an ABR. We have Area 51, Area 0, Area 52, 53. Area 0 is, of course, the backbone area. We see, though, that Area 51 is configured as a stub area. We then see that Area 52 is configured as a stub with the No Summaries flag. This flag indicates that the area is a total stub. No summary LSAs will be advertised into this area. Only a default route will be advertised. Finally, we see that Area 53 is configured as an NSSA. The NSSA configuration hierarchy has its own configuration properties available as well. The No Summaries flag here indicates that the area will behave just like a total stub, though still will allow Type 7 LSAs. The default route advertised by the ABR into the NSSA will have a starting metric of 10, as we see with the default metric command. Each of these areas are configured to have a single interface within. This is all the configuration that is needed to enable OSPF, simply defining an area ID and adding an interface to the area. Using the Show OSPF Interface Detail command, we can see the detailed configuration and operational information about each interface on the local router which is participating in OSPF. The item here I want to draw your attention to is the not stub and stub flags here. The stub flag must be configured on all routers in the stub area. If there is a mismatch between routers about the area type being a stub or not, the OSPF adjacency will not come up. In this case, we see that the GE002.0 interface is the DR for its broadcast domain and is a member of Area 0. Area 0 is not a stub area. The interface below, GE001.0, is a member of Area 51, and Area 51 is configured as a stub area. Let's take a look at the other 2 configured interfaces on this router. GE003, we see here, is configured in Area 52. This area is also a stub. Recall in our configuration a bit earlier that this area was configured as a totally stubby area, using the stub no summaries command. In this output, we see that the totally stubby area is identical to a regular stub area. However, no summary LSAs, except the default route, will be advertised into the area. Finally, we have GE004.0. This interface is a member of Area 53, which is configured as an NSSA. We see in the flag here that the area is shown to be a stub with the NSSA flag, and is how we can validate the intended configuration is taking effect. I appreciate you working through this lesson with me to cover the router and area types in OSPF and the configuration and monitoring of OSPF areas to enhance the scaling of our OSPF domain. I hope that this lesson has been informative for you, and I would like to thank you for viewing.